We're going to talk about some possible MDP optimization criteria. And I guess this isn't really an optimization criterion, but we talked about exploring randomly being problematic because you can have MDPs that look like this, where there's a chain and you have to keep taking some specific action to get to the high reward state. And if you're always choosing actions randomly, then the probability you even ever reach that is exponentially small. So we have to be a little bit careful. For example, in this MDP, it's not really clear what to do from this state.
From which state? That state? No, it's pretty clear what to do from that state. Go left.
Oh, okay, sure. No, I mean, in the reinforcement learning setting, we have just two actions. If we choose wisely, as you just did, then we end up in this state and we get reward, and that's yay. If we choose not wisely, then we get stuck in this trap state and we get bad reward forever and there's no way out. And so in the reinforcement learning setting, we don't know which of those, where the different arrows are pointing until we try it. So it's a little bit unfair to say what we should be doing is maximizing all possible reward values, right? Because it could be that we get ourselves into a position where we just can't anymore. So here's what I advocate. Remember we talked in the bandit case about a mistake bound, the idea of the number of times you pull an arm that's not the right arm to pull is bounded by some polynomial. It turns out that works out really nicely in MDPs as well. So the idea is that, think about this state here in this trap example. It has only one action choice from this state. So what's the right action to choose from here?
The one action?
Yeah. So we're not wrong.
True.
Right? And so in fact, no matter what in this particular MDP, the total number of mistakes we could ever make is 1, right? We might make this wrong first action, and then we're making optimal actions thereafter. I mean, again, optimal is relative to the state that we're in, but we're in the state that we're in.
Oh, that's kind of deep. Okay.
Thanks. So the criterion that I'm going to advocate for here is that what we're going to do is count the number of epsilon suboptimal actions. That is to say, the number of times that we're in a state, we choose an action, and that action in that state was not epsilon close to the best action in that state, that we want that to be bounded by some polynomial in, let's say, 1 over epsilon, 1 over delta, the number of states n, and the number of actions in each state k.
Okay. Okay. So the actions are like bandits. I like where this is going.
A little bit. We're going to bring it all together. So this wasn't really an analysis of different criteria. This was basically me just trying to justify one criterion because it has some nice properties. It lets you deal with the fact that there can be trap states, and that doesn't hurt us in the learning setting. And, well, we're going to have to come up with an algorithm that's going to deal with this randomness case, this you can't explore randomly idea.
Okay. So I think there should be a fourth criterion, by the way, which was inspired by your recommending that I listen to William Shatner sing, which is the Kobayashi-Maru criterion, which is we minimize the number of times we have to cheat.
I do not remember recommending that you listen to William Shatner.
But everyone should.
Okay, but that's a separate issue. So minimize in the Kobayashi-Maru test, he reprogrammed it so that he could win, even though you couldn't win. So this is kind of like that in that we're defining winning. That's not really like that, but it's defining winning to be doing the best thing given the state that you're in, and it's not actually penalizing you for having done something really stupid for having gotten into that state, as long as the total number of really stupid things is bounded.
Everything really does come back to Star Trek. Okay, I buy that. 3 and 4 are the same.
Well, we can't cheat. You can't cheat in reinforcement learning.
Oh, I beg to differ.